Hello, I'm Dr. Bradley Batista, a principal scientist at Tanzle. Tanzle has been developing cloud infrastructure that strives to be generic and fast, using reactive tools and custom data indexing to combine data and algorithm pipelines into streaming data pipelines that may be hyper-focused or generalized depending on need. As you know, the overarching scenario is a hypothetical scenario where a cruise ship becomes stranded in a remote part of Alaska. Tanzle's sub-scenario involves managing streaming data coming from raw telemetered and broadcast environmental sensor and marine traffic data feeds. But our first major challenge is lack of data. Here we can see the past efforts of the U.S. mapping coordination, and now the ongoing and planned efforts. Clearly, there is an effort to map Alaska, and we are too early to use that data. So, we will use the same types of streaming data coming from another area to show our approach. Let's start with algorithmic map tiles. What are they? Algorithmic map tiles are similar to conventional map tiles, only the pixel values are determined in real time, allowing for new data to automatically update the tile set. This allows us to maintain consistent metadata across raw and simplified data, and it allows us to bend and break tile specs, rebuilding them as necessary to fit the needs. We have been watching AIS and environmental data switch between entities, seen as yellow markers, and as map tiles colored by algorithm results mapped into color space. And we can apply cross correlations between data sources as we see in this air-water temperature differential. And we do this because it maintains insight and awareness across all data, whether it is being curated or simply streamed as is. It also provides a valuable tool for discovering unknown relationships between the data. Here's an example showing how AIS shipping traffic and weather derived from a fleet of drifting buoys intersect. The heat maps may be dynamically filtered and rendered to a subset of the data in space, time, or both. So if there is a newly observed footprint of one in the other, something common in situational awareness, then we can explore past and present conditions to inform and update predictions. Building upon the example, we can explore other data such as video, as we are doing here with the Department of Transportation traffic cameras provided by way of TrafficLand, where we may see the actual vessel to further understand the conditions leading to its footprint in the weather data. And here we can look at other examples. Vessel-to-vessel interactions in the top left panel revealing several patterns, including search and recovery and/or geophysical survey, pilot-to-container vessel, and ferry boat activities. Filtering to just the ferry boat in the top right panel reveals the ferry schedule and the time scrubber, seen as the histogram in the bottom of the panel. The lower left panel shows a container ship moving offshore just after an encounter with a pilot and just prior to going dark. That scenario requires us to leverage satellite data feeds to address, as we are seeing here. Unfortunately, we do not have access to relevant data and are using the International Space Station video feed as a placeholder. This is the second major challenge that we encountered: public access to relevant data that does exist. On the technical end, we did find limitations in the Web Mapping Service Time Dynamic Spec, or WMST spec, and we're able to bend and manipulate parts of the spec to get Cesium to use our algorithmic map tiles, which are rendered on the fly. We met another major challenge in trying to serve our WMST layers with external front ends. We tried this with QGIS mainly, learning that it doesn't fully support web-based authentication through bearer tokens, nor does it fully honor capabilities parsing in the WMST spec. We didn't have time to investigate which bleeding edge release of QGIS and which version of the WMST spec could work and still be stable, and this is something to address in the future.